Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome to lecture 5 in week 5. Today we talk about what are ideal thermoelectrics, some of the intricacies between Carnot and Curzon-Ahlborn Limit. Should I start?
Oh, we're okay.
Oh, sorry.
Yeah, just start from the top again.
Okay. Welcome to week 5, to lecture 5 of the week 5. Today we are talking about some ideal aspects of thermoelectrics, Carnot versus Curzon-Ahlborn limits for efficiency and how they apply to thermoelectrics, and a few open questions, at least for me, related to thermoelectrics. I think it's a good way to end this. We always discuss energy conversion. The ultimate limit is Carnot limit. And Carnot limits in standard pressure volume considers 2 isothermals and 2 adiabatic, and the working fluid exchange energy with the reservoirs during the isothermals. That's where the energy exchange is happening, and the work is produced during the adiabatic. One thing that is always important to point out is Carnot limit applies to near reversible. That means the output power goes to 0. And that actually comes from Carnot's key intuition of how engine should work the best. In his original book in 1824, Reflections on the Motive Power of Fire, he discussed that the production of the motive power is then due to the steam engine, not to an actual consumption of the caloric, but to its transportation from a warm body to a cold body, that is, to its reestablishment of equilibrium. At the time, of course, they didn't know that heat is random vibrations of atoms. They didn't even know atoms. They thought heat is a caloric that moves from a hot object to the cold object. But through careful observation, Carnot had said that in order to get the highest efficiencies employed to realize the motive power of heat, there should not occur any change of temperature which may not be due to a change of volume, because that's how you do work. And that's how he came up with the what we call today Carnot cycle. Basically, during this adiabatic compression and expansion, the work is performed on a piston, but when the heat is coming from the hot reservoir to the working fluid, there is no work done. So you want to minimize any losses. That's the reason delta T is almost 0. So the amount of heat in to heat out goes to 0. That's what gives the 0 output power. In 1975, Curzon and Ahlborn had a very interesting article. They basically said, if we want to make this heat engine to have some output power, and we are interested in efficiency at maximum output power, we need to make a finite amount of heat transfer. Even though we don't do work with it, that accelerates how fast this working fluid comes in equilibrium with the reservoir. Intuitively, you would say the temperature on the hot side of this should be lower than the temperature of the reservoir, but not too low, because if it's too low, then it's close to the temperature on the cold side, and the efficiency of the engine will be small. But if the temperatures are too close, then heat flux is too small. So it kind of seems intuitive there should be an optimum temperature, intermediate temperature, and that optimal intermediate temperature is like a geometrical average. Basically, the limit of efficiency at maximum output power, according to Curzon-Ahlborn, is 1 over square root of temperature of the ambient divided temperature of the source, which is different from Carnot, which is 1 minus TA divided by TS. And in this paper, we derived that the same thing can be done for bulk thermoelectrics, and that's something we want to see today. Now that we have looked at some of the fundamentals, let's go back to this optimum thermoelectric. This is the Sofa and Mahan's paper, which was described by Professor Lundstrom in week 2. A delta function has the best thermoelectrics. The key issue is when you have a delta function transport, can you really use Boltzmann transport? What happens in terms of coupling with reservoirs and so on? A very interesting but different approach was taken by Tammy Humphrey and Heiner Linke in this paper in 2005, that they said if you consider a hot material in contact with cold, assume you have an N-type material, so this shaded region is supposed to show the occupation density, and these are the conduction and the valence band. What Humphrey and Linke pointed out is that we always say when you have a hot in contact with a cold, in an N-type material, electrons flow from hot to the cold. And when you have hot to the cold for a P-type material, holes flow from the hot to the cold. But if you look at within the energy axis what flows, what we consider our intuition happens for high energy electrons or high energy holes. There are some low energy electrons that go opposite. And this is actually this opposite going carriers is the reason for electronic thermoconductivity. This is the reason for the Widman-Franz law. But there is a single energy level, which was shown in this case by this green line, very important. At that energy level, the occupation probability on the two sides, hot and cold, is the same, even though they have slightly different voltages. They point out, it's very simple math, if you take the expression for the Fermi-Dirac distribution, on one side you put T hot, the other side you put T cold. But in the energy one, on one side you put E0, the other one E0 plus some open circuit voltage. At that specific energy E0, the two could be equal, and then you get a voltage that is divided by band gap, which is basically Carnot factor. So the intuition here is constant occupation of states give you an equilibrium. So despite the temperature and electrochemical potential gradients, these are finite, non-zero, at that energy you have equilibrium. So if the two hot and cold objects could only talk through this narrow channel, then they are in equilibrium, and any small perturbation near that can give you Carnot level efficiency. That's different from the way Sofo and Mahon approached it, because they did not consider this effect that happened at finite temperature differences between the two reservoirs. Here is a picture of kind of ideal material according to Humphrey and Linke. Here are the Fermi-Dirac distribution versus energy. On the cold side, very sharp. On the hot side is more gradual. But at a single energy level, there is a constant occupation for everywhere in the material. Assuming some sort of graded superlattice, maybe you can achieve that. But of course, that's very hard to do in practice. But fundamentally, is an interesting limit to remember. There have been other studies. What are the thermodynamic analysis of a single level thermoelectrics? If I have a single level atom with two reservoirs, hot and the cold, using a standard type of quantum master equations and Landauer type formalism, Esposito and all, derive expressions for the efficiency, and they also obtained some sort of Curzon-Ahlborn expression. One thing they neglected is as soon as a single energy level starts to couple to reservoir, fundamentally that cannot stay quantized states. There is a broadening that happens. This broadening was taken into account by Nakta Potomkin et al. From Heiner Linke's group in 2010. A similar case, a single level in contact with two reservoirs, but here the broadening is taken into account, and the analysis is exactly similar to what you learned from Professor Datta. Neglect phonon mediated transport, but consider the level broadening. What happened here is versus gamma, the width, the broadening of this energy level, what is the maximum power and what is the efficiency? Of course, the narrower is this energy level, the closer you can approach the Carnot limit, but at delta function you approach Carnot, but then the output power is zero. As I said, there is zero rate of exchange with reservoir. So to have some rate of change with reservoirs, you want to get a finite width, but then when you do a finite width, you lose on the efficiency because kind of electronic contribution to the conductivity goes up. Here is the optimum. The efficiency at maximum power happens at something about ZT of, KT, 2.25 KT width, so that's important. And so this is kind of a full range of applications. You see how a single level could be analyzed from a fundamental thermoelectric point of view. Interesting, you get the Curzon-Ahlborn limit that happens for efficiency. What is interesting is the same analysis for single level could be applied to the case of bulk material. Here is a paper came out in 2012 by Kazuyazawa et al. Again, here we are not talking about the single level. Is a bulk thermoelectric, has a Seebeck coefficient, electrical conductivity, and thermoconductivity. The question is, we put it in the contact with the source and ambient with two finite reservoir that happens all the time. This is something we did in week 3 for the system analysis. The Carnot limit is the factor that we all know is 1 minus T ambient divided by T source. That's a line in this graph when you plot it as a function of T ambient divided by T source. And here are the curves that you get for different case of reservoirs. So in this paper by Esposito, he derived two limits, eta plus and eta minus. These two are derived as if one of them is just Carnot limit divided by 2 and the other one is higher than Carnot limit divided by 2. He derived these two limits assuming different scaling of the thermal resistances. Basically, Esposito said that thermal resistances with the hot and cold reservoirs are not symmetric. In the case of a very low contact resistance with the cold reservoir, you can get higher efficiency, or I guess other way around. Here are the actual efficiencies of today's power plants, thermal plants that we have within the two limits. When we did the analysis for thermoelectrics in this paper, for bulk material, no matter what was the asymmetry, we did not get these two limits. We got the same Curzon-Ahlborn limit. And of course, when ZT is not infinity, this is what you get. So it's significantly less than that. But what is important is this Curzon-Ahlborn, efficiency at maximum power, could be derived in a variety of cases, going from single-level thermoelectrics all the way to the bulk, and according to this latest paper, is independent of asymmetry of the thermal contact with reservoirs. So I want now to mention some of the open problems, some of the issues where I think there is potential to make impact. One interesting paper came out in 1997 by Cronin-Vining. It's called Thermoelectric Process in MRS Proceedings 97. It's not highly cited, but it's quite interesting because it gives a direct analogy between a mechanical cycle and a thermodynamic cycle. And in that paper, he says that ZT, it can be considered as this gamma parameter that is known for ideal gases and so on, ratio of the heat capacity at constant volume and constant pressure. And if now you plot ZT versus temperature for the typical material we know, bismuth, antimonite, bismuth telluride, lead telluride, silicon, germanium, we know ZT of 1. But now plot on the same graph this gamma pi, which will correspond to 1 plus ZT, by the way. So you see this axis is more than the other axis by unit. You see for Freon 12, which is used in mechanical system refrigerators, at the temperature we are using, this is diverging because there is a phase transition. So a comment that Vining made is that if we could create a first order phase transition, if there is some latent heat in the transported energy of the electron gas, the efficiency of thermoelectric energy conversion could be significantly increased if we take a mechanical engine and not operate it near this type of phase transition. Their efficiency are low, similar to other thermoelectrics. Can we have a phase transition electron gas in a form that is mobile? Of course, if a phase transition happens and electrons are bound to a location, then you need to move physically that electrons, and that's not what we want on a thermoelectric device where you want to have no moving part. But fundamentally, there is nothing that prohibit having the possibility to have some sort of latent heat developed for the electron gas, but that will be a very interesting physics. Another open problem seems kind of unrelated, but if I have a material and I excite it with some energy pulse, like a pulse laser heating on the surface, and I ask the question, how much energy propagates in the material, energy density propagation at different time and different locations, through this interface impulse response excitation, you can define a Green's function, and in the momentum space and omega space, it's given by this complicated relation. This is coming from Sriram Shastri, but this relation tells you that there are three key parameters. A relaxation time for energy carriers, this is a function of wavelength. You have a heat diffusion coefficient, dq, and you have a charge diffusion coefficient, dc. The diffusion coefficient for heat and charge could be different because each carrier carries the same charge, but it carries different amount of internal energy, so it can have a different heat diffusion coefficient. What is interesting is, so these type of equations, the first term is the diffusion for heat, the second one is diffusion for charge, but interestingly, the diffusion for heat and charge are coupled by this parameter psi, which Shastri derived this factor is Zt divided by 1 plus Zt. He derived it through his expressions. It's a high frequency limit factor, but Zt is like the Hall coefficient, should not have a high dynamic response, is a ratio of the material properties, but it's important that Zt divided 1 plus Zt is inherent coupling between charge and energy transport. What this means is that if we do pump probe experiment on a thermoelectric material, usually we can talk about heat propagation or charge generation, but in the thermoelectric material the two are strongly coupled, so there could be an interesting new type of devices you can make using this coupled transport regime. One other open area that I want to emphasize is thermoconductivity of the superlattice. Early on in thermoelectrics, it was claimed that any type of multi-layers of materials you can put, scatters phonons, is good for thermoelectrics. Through a collaboration with Ed Kroc, Karan Majumdar et al., for quite a few years, we grew hundreds of superlattices based on silicon and silicon germanium. And this is a typical result we found. This is the measured thermoconductivity versus temperature, layers that are 2-3 micron. The measurement was done using 3 omega that you learn in week 3. For silicon germanium of alloy, silicon at room temperature thermoconductivity in this case is about 8 or 9. When we add different superlattices with 30% germanium, with a total period of 300 angstrom down to 45 angstrom, our thermoconductivity was always higher than the average alloy. And that was a concern, is that we wanted to do some energy filtering, but we wanted to also lower thermoconductivity. And as you saw, this higher thermal conductivity actually was a detriment. As a result, we didn't get so much better refrigerator with superlattices. Again, that was one of the lectures you saw earlier on. But we thought maybe the problem is the acoustic impedance mismatch between silicon layer and silicon germanium with 30% germanium is not substantial. Maybe we need just to increase, before I go on, one thing I should mention is, do these are really superlattices? Do we behave as changing the phonon spectrum? And the answer is yes. Phonon minibands were observed. How do you observe that? You put a transducer aluminum. We discussed with a pump laser, you can heat it up from the decay measure thermal conductivity. But in addition, this vibrates and it creates acoustic waves that are going back and forth. Here is the change in surface reflection versus time where the thermal decay has been subtracted. And you can see very nice oscillations. The period between oscillations on the order of, you see about maybe 50 picoseconds matches exactly the time it takes for the acoustic waves to go from the cap layer to the superlattice come back. The question is why this oscillation of this specific frequency happen. If you take FFT of these two peaks, you see a peak at 280 gigahertz, another one at 527 gigahertz, and these two are exactly what you expect for a calculation of the phonon reflection coefficient based on the Kramers-Kronig relationship. So you have phonon minibands, superlattices, interfaces are large, good enough to see these. Of course, we see these at frequencies, wavelengths that are very low. These are not the thermal phonons, but they still are present, but we don't see their thermal conductivity. Later on, we said, let's just increase the amount of germanium, in this case 60% germanium, and see what happens to the superlattice thermal conductivity. Here, the acoustic impedance mismatch is larger. We saw significant reduction below the alloy limit. That was a good sign. We thought maybe this was the trick. We just needed to improve the acoustic impedance mismatch. But the end result is, because the lattice constant of 60% germanium is so different, this actually material is very defective. Of course, there is no law that says a good-looking material should always have better performance. So we made devices and we measured cooling. The cooling of these superlattices was better than this. So really, by creating defects, not only you lower thermal conductivity, but you make the life for electrons much harder. And the last point is a miniature refrigerator. We discussed early on, any fundamental refrigerator, at one side you cool, the other side you heat. But in a tiny device, you can think of cases where on the other side, the excess energy is given by light. And in some early papers, we emphasize that this type of optothermoelectric devices are possible. Of course, the light cannot be coherent because then you reduce the overall entropy, but the randomness of the light, different polarization, different wavelength, give the possibility to make a device that cools but also emits light. Of course, it's very challenging to take the light out. That's the key problem here. Let me summarize this lecture. We discussed about Carnot versus Curzon-Ahlborn efficiencies. We revisited Professor Datta's lectures in first week about single-lever thermoelectrics from different point of view, from Sofa and Mahon versus Humphrey and Linke about what is the inhomogeneous kind of single level. We look at optimum broadening and the thermodynamic arguments, and then we discuss some open questions related to phase transition electron gas, coupling of charge and energy transport, superlattice thermal conductivity, and optothermoelectric devices. In the last lecture of the week 5, we will summarize what you learned this week, and I look forward to see you.